the Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program is an introduction to plastic injection molding. Injection molding is the most common method of producing parts out of plastic material. The process involves injecting molten plastic at high pressure into a mold shaped in the form of a part. Once this plastic cools and solidifies, the mold opens and the part is ejected. Injection molding is an extremely versatile process that can produce parts with holes, springs, threads, hinges, and undercuts in a single operation. Injection molded parts can be simple or complex, and can be solid, foamed, reinforced, or filled. They can be small or large, thick or thin, flexible or rigid. Injection molded parts also lend themselves to endless decorative effects. They can be polished, textured, hot stamped, plated, colored, or clear. No other manufacturing process offers the range of capabilities injection molding provides. To better understand the injection molding process requires understanding some properties inherent in plastic itself. The simplest definition of a plastic is any natural or synthetic polymer that has a high molecular weight. There are two types of plastics: thermoplastic and thermosets. Thermoplastics undergo a reversible change from solid to liquid when heated, and can be cooled and reground for reuse over and over again. Thermosets undergo a chemical reaction between two reagents when heated and achieve their strength through the interlocking chemical bonds. Once molded, thermosets cannot be resoftened. While thermosets are injection moldable, most materials used in injection molding machines are thermoplastics. Injection molding plastics is extremely complicated because of the infinitely changing pressure, temperature, and velocity inside the mold. These molding conditions directly affect the properties of each molded part. A change in any of the conditions will alter the parts produced. There are four primary elements that influence the plastic injection molding process: the molder, the material, the injection machine, and the mold. This video focuses on the latter two, the injection machine and the mold. There are a variety of injection molding machines in use today. The vast majority of these machines are hydraulically actuated and have 3 platens. But newer styles, such as 2-platen injection molding machines and electric injection molding machines, are now gaining market acceptance. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. Most injection molding machines are horizontally oriented, but vertically oriented molding machines are available. These vertical machines are primarily used for insert molding. All injection molding machines are a combination of 2 systems, an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are 2 types of injection mechanisms: the reciprocating screw, which is the most common, and the 2-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. The screw consists of 3 zones. The first zone, which is 1/2 of the screw, is called the feed zone. It has a constant flight depth, which forces the material together and rids it of air. The second zone, called the melt zone, has a decreasing flight depth, which reduces the plastic volume. This causes the plastic molecules to rub harder against each other, plasticizing the material. The melt zone leads to the third, or metering zone. The metering zone has a constant flight depth much smaller than that of the feed zone. This section acts as a pump. The tip of the screw has a one-way valve which lets the material flow only towards the nozzle end. The force of the plasticized material pushes the screw back as it turns. This builds a chamber of plastic in front of the screw. When enough material for the injection shot is melted, the screw stops and pulls back to decompress the material. For injecting the material, the one-way valve closes as the screw is hydraulically pushed forward by the injection cylinder. This sends the molten material through the injection unit's nozzle and into the injection mold. The primary speed and the injection pressure, called the packing pressure, is high, usually around 20,000 psi, but sometimes reaching up to 30,000 psi or higher. A secondary lower pressure is applied shortly after the initial injection. At the time of injection, the material's temperature ranges from approximately 320 to 600 degrees Fahrenheit, or 160 to 320 degrees Celsius. Once the plastic solidifies, no more pressure can be exerted upon it in the mold. The reciprocating screw then begins to rotate again, melting material for the next shot. The 2-stage screw-type machine has a screw which constantly forces melted resin into a second straight bore cylinder with its own plunger. When the correct amount of material has been transferred, the screw stops turning, and a valve closes, separating the cylinders. The plunger pulls back to decompress the material, which is then injected into the mold. The function of an injection molding machine's clamping system is to keep the plastic material from leaking out or flashing at the parting line of the mold's cavity and core. The clamping system of the injection molding machine has 2 configurations. One is a fully hydraulic system where the total clamping force is generated by the hydraulic clamping cylinder. The second is a toggle system where a much smaller hydraulic cylinder is used in conjunction with a series of toggle levers to provide the full clamping force. Injection molding machines are designated by their clamp tonnage, which is the amount of sealing force a machine can produce against the high pressures generated during the injection process. Platens are large, thick blocks of tough steel which will not deflect enough to affect the injection process. There are 3 platens on most injection molding machines: a stationary platen, a movable platen, and a rear stationary platen. The stationary platen has a hole directly in line with the injection cylinder's nozzle. The cavity side of the mold, sometimes called the A or stationary side, is attached to the stationary platen. The stationary platen also anchors one end of the machine's 4 tie bars. The movable platen holds the core side of the mold. This is also referred to as the ejection, knockout, or B side of the mold. This movable platen moves back and forth on the tie bars. As the mold opens, the ejection system expels the molded part. The rear stationary platen holds the other end of the tie bars, anchoring the entire clamping system. Injection molding machines are designed not to operate unless the front and rear safety gates are closed. This limits access to the platen area while the machine is in operation. A safety drop bar is required on injection molding machines. It drops down between the platens when the safety gate is open, so that the machine cannot close upon a person. This is in addition to other hydraulic and electrical safety systems. When machines are run in a semi-automatic mode, the operator removes the part, then closes the gate, starting the next cycle. In automatic operation, there is no operator intervention, and parts either fall down into a container or onto a moving belt or other device, or are removed by a robot. The plastic injection mold is a vital component of the injection molding system. The injection mold both determines the shape of the desired part or parts and acts as a heat exchanger to draw heat away from these parts. In addition, the injection mold vents trapped air or gas and ejects the cooled parts. Molds are usually produced from special mold steels, but are also manufactured from materials such as beryllium copper, stainless steel, aluminum, brass, Kirksite, and epoxy. Molds are manufactured using a variety of methods, including machining, EDMing, casting, and others. Once manufactured, mold cavities and cores are generally heat-treated. In addition, the cavity and core surfaces are often plated or coated to help resist wear, corrosion, and to aid in part release. As the injection mold is installed in a machine, a locating ring, which seats in a hole in the stationary platen, serves to locate and center the mold. The mold sides are secured by clamps which are screwed into tapped holes covering the platens. Leader pins and bushings align the mold. One pin is asymmetrical to prevent improper assembly. The nozzle of the heating cylinder seats on a sprue bushing which is centered in the locating ring. The sprue bushing has a tapered hole in its center. This directs molten material from the injection machine's nozzle into the mold's runner system or directly into the mold's cavity. A mold's runner system is the channel or channels through which the melted thermoplastic flows to reach the gate. The gate is the interface linking the runners to the cavity which forms the part. If the molten plastic goes directly from the sprue bushing into the part, it is called a sprue gate. Some other gate types that use a runner system include the edge gate, which is the most common, the submarine gate, the tab gate, the ring gate, and the fan gate. Vents are ground on the parting line of the mold to remove the air displaced by the material flowing into it. The size, number, and location of these vents are determined by the molder. They are primarily established by the part geometry, gate location, type of injection material, viscosity of the material, and the rate of injection. Built into the mold are channels for circulating water, which is the mold's primary cooling medium. The water is pumped continuously through the mold to and from a cooling unit, removing the heat and solidifying the part. Proper cooling provides a consistent temperature and coolant flow rate, which contributes to controlled shrinkage, part strength, and other properties. The speed of the injection molding production cycle is controlled by the efficiency of this cooling system. Aside from producing acceptable parts, efficient cooling is the most important factor of the injection molding process. Once the part has had time to cool and solidify, the mold opens at the parting line, which may be flat or regular, or irregular. Since the force of the molten plastic against the mold creates significant friction, a knockout system is required to aid in part ejection. This is usually in the form of knockout pins. In some molds, a sprue puller aids in removing the molded plastic from the sprue. This material can then be reground for reuse. The knockout pins and other mechanisms are mounted between knockout plates, which ride on their own leader pins and bushings in a pocket on the ejection side of the mold. In most cases, they are activated by pneumatic or hydraulic cylinders, although older machines still use mechanical knockouts. Some other types of ejection methods include using a stripper plate, a stripper ring, air ejection, jiggler pins, mechanical cams, cams operated by a hydraulic cylinder, or by a pneumatic cylinder. Over time, many different mold designs have been developed that meet specific injection molding requirements. These mold designs include the Cold Runner 2-plate mold, the Cold Runner 3-plate mold, the Hot Runner mold, and the Insulated Runner mold. The Cold Runner 2-plate mold consists of 2 plates with the mold cavity and core mounted on them. The Cold Runner system molds the sprue, runners, and gate along with the parts. After ejection, the parts are separated and the rest reground. The Cold Runner 3-plate mold uses 3 plates to mold the part. These plates include the stripper plate, which contains the sprue, the middle or cavity plate, which holds the cavity, runner, and gate, and the movable plate, which holds the molded part. This type of Cold Runner mold design automatically separates the runner system from the part as the mold opens and is very easy to automate. The Hot Runner mold uses an electrically heated manifold that keeps the molten thermoplastic in the runners at the same temperature as the heating cylinder. The heated runner system is contained in a plate of its own and does not open during the molding cycle. Because of this, Hot Runner molds generate no runners or sprues. For this reason, Hot Runner molding, also known as runnerless molding, is fast and efficient. The Insulated Runner mold is much like the Hot Runner mold, but it uses a large diameter runner. During injection, the outer surface of the runner freezes. This insulates the center material, keeping it at the molding temperature. The type and location of machine controls are dependent upon the injection molding machine. These controls can vary from electromagnetic relays and timers to computer-driven solid-state devices. These computers not only control the process, but perform other functions such as quality control, real-time reject recognition, fault analysis, record keeping, and instant accurate setup. After the molding conditions are set, the molding machine uses the computer to control the sequence of operations. The controller's instant feedback system provides better process stability than can be achieved by humans. Computer controls can provide real-time readouts of system conditions from multiple locations so that one engineer can monitor an entire plant. Controls can record every molding condition for each injection cycle and keep a log of machine activity. This data can be used to analyze downtime and machine efficiency. Additionally, computers are used for various activities throughout the design and construction of the injection mold. Computer software packages can approximate and visualize various conditions within the injection mold, providing valuable feedback for the part and mold design. These packages can also convert designs into mold drawings and provide programming data for automatic machining of the mold base, cavities, and cores. Let's review the material contained in this videotape. Injection molding is the most common method of producing parts out of plastic material. The process involves injecting molten plastic at high pressure into a mold shaped in the form of a part. Once this plastic cools and solidifies, the mold opens and the part is ejected. Injection molding is an extremely versatile process that can produce parts with a wide range of attributes. There are an extensive variety of injection molding machines in use today. These machines are all a combination of two systems, an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are two types of injection mechanisms: the reciprocating screw, which is the most common, and the two-stage screw. The function of an injection molding machine's clamping system is to keep the plastic material from leaking out or flashing at the parting line of the mold's cavity and core. The clamping system of the injection molding machine has two configurations: a fully hydraulic system and a toggle system. Injection molding machines are designated by their clamp tonnage, which is the amount of sealing force a machine can produce against the high pressures generated during the injection process. The injection mold both determines the shape of the desired part or parts and acts as a heat exchanger to draw heat away from these parts. In addition, the injection mold vents trapped air or gas and ejects the cooled parts. The speed of the injection molding production cycle is controlled by the efficiency of the mold's cooling system. Aside from producing acceptable parts, efficient cooling is the most important factor of the injection molding process. The type and location of machine controls are dependent upon the injection molding machine. These controls can vary from electromagnetic relays and timers to computer-driven solid-state devices. These computers not only control the process, but perform several other functions. Additionally, computers are also used for various activities throughout the design and construction of the injection mold.